A similar phenomenon had been observed in 1980 by Ray White and Arlene Wyman, who, looking at a different gene, had shown that such repeats varied in number from individual to individual. Jeffries determined that his repeats were junk DNA, not involved in coding for protein. But he was soon to discover that this particular junk could be put to good use. Jeffries found that this short stretch of repeating DNA existed not only in the myoglobin gene, but was scattered throughout the genome. And although the stretches varied somewhat from one repetition to the next, all of them shared one short, virtually identical sequence of some 15 nucleotides. Jeffries decided to apply this sequence as a probe. Using a purified sample of the sequence tagged with a radioactive molecule, he could hunt for the sequence genome-wide. With DNA from the genome laid out on a special nylon sheet, the probe would stick down by base pairing wherever it encountered its complementary sequence. By placing the nylon on a piece of X-ray film, Jeffries could then record the pattern of radioactive spots. When he developed the film from the experiment, he was astonished by what he saw. The probe had detected many similar sequences across a range of DNA samples. But there was still so much variability from one sample to the next that even among ones taken from members of the same family, you could tell the individuals apart. As he wrote in the resulting paper in Nature in 1985, the profile provides an individual-specific DNA fingerprint. Jeffries' choice of the term DNA fingerprint was quite deliberate. This technology clearly had the power to identify an individual, just like traditional fingerprinting. Jeffries and his staff obtained DNA samples from their own blood and subjected them to the same procedure. The images on X-ray film, as expected, made it possible to distinguish unambiguously between people. He realized the range of potential uses was extensive. In theory, we knew it could be used for forensic identification and for paternity testing. It could also be used to establish whether twins were identical, important information in transplantation operations. It could be applied to bone marrow grafts to see if they'd take it or not. We could also see that the technique would work on animals and birds. We could figure out how creatures are related to one another. If you want to understand the natural history of a species, this is basic information. We could also see it being applied to conservation biology. The list of applications seemed endless. But the procedure's first practical application was stranger than any Jeffries had anticipated. In the summer of 1985, Christiana Sarba was at her wit's end. 2 years before, her son Andrew had returned to England after visiting his father in Ghana. But at Heathrow, British immigration authorities had refused to admit the boy, though he had been born in Britain and was a British subject. Denying that Sarba was his mother, they alleged that Andrew was in fact the son of one of Sarba's sisters and was trying to enter the country illegally on a forged passport. After reading a newspaper report about Jeffries' work, a lawyer familiar with the case asked the geneticist for help. Could this new DNA test prove that Andrew was Mrs. Sarba's son and not her nephew? Well, the analysis was complicated by the fact that neither the father nor Sarba's sisters were available to give samples. Jeffries prepared DNA from samples taken from the mother and 3 of her undisputed children. The analysis showed that Andrew had the same father as the other children, and that Sarba was his mother. Or, more specifically, the chances were less than 1 in 6 million that one of her sisters was his mother. The immigration authorities did not challenge Jeffries' results, but avoided formally admitting the error by simply dropping the case. Andrew was reunited with his mother. Jeffries saw them afterward. The look of relief on her face was pure magic. But would the technique work with blood, semen, and hair, the body tissues typically found at crime scenes? Jeffries was quick to prove that it could indeed, and soon his DNA fingerprints would gain worldwide attention, revolutionizing forensic science. On a Tuesday morning in November 1983, the body of a 15-year-old schoolgirl named Linda Mann was found on the Black Pad, a footpath outside the village of Narborough, near Leicester in England. She had been sexually assaulted. 3 years passed with no arrest in the case. Then it happened again, on a Saturday in August 1986. The body of Dawn Ashworth, another 15-year-old, was found on 10 Pond Lane, another footpath in Narborough. The police were convinced that the same man had committed both murders and soon accused a 17-year-old kitchen assistant. But while confessing to the Ashworth murder, the suspect denied involvement in the earlier case. So it was that the police consulted Alec Jeffries to confirm that their suspect had killed both girls. Jeffries' fingerprint analysis contained both good and bad news for the authorities. Comparison of samples from the two victims showed that the same man had indeed carried out both murders, as the police believed. Unfortunately for the police, the same test also proved that the kitchen worker in custody had not murdered either girl, a result confirmed by other experts the police called in. The suspect was released. With their only lead now blown and worries rising in the local community, the police took an extraordinary step. Confident that DNA fingerprinting would yet prove the key to success, they decided to request DNA samples from all adult males in and around Narborough. They set up stations to collect blood samples and were able to eliminate a great many candidates by the traditional and cheaper test for blood type. The remaining samples were sent for DNA fingerprinting. A good Hollywood version of the story would, of course, have Jeffries identifying the true killer. And it did happen that way, but not without a further plot twist, also worthy of Tinseltown. The culprit initially eluded the genetic dragnet. When faced with providing the mandatory sample, Colin Pitchfork, pleading a terror of needles, persuaded a friend to furnish the sample in his stead. It was only later, when the friend was overheard telling of what he had done, that Pitchfork was picked up and thus gained the dubious honor of being the first criminal ever apprehended on the basis of DNA fingerprints. The Narborough case showed law enforcement agencies worldwide that DNA fingerprinting was indeed the future of criminal prosecution. And it would not be long before such evidence was first adduced in an American legal proceeding.